Hello learners, welcome to the series of lectures on functional analysis. In the last lecture, we defined what is known as the subspace nonlinear space, and we also saw what is known as the direct sum, and towards the end of the last lecture we introduced what is known as the quotient nonlinear space. In fact, we defined what is known as the quotient space. Today we are going to introduce the concept of the norm on a quotient space, right. So, let us recall, if you have a closed subspace Y of a nonlinear space X, then this X mod Y stands for all cosets X plus Y such that X belongs to X, right. So, today we are going to define what is known as the norm of a coset. The norm, well, I will write it as X mod Y to distinguish that this represents the norm on the X mod Y. It is defined as infimum over X plus Y, in fact norm of X plus Y. So, this norm is on X such that Y belongs to Y. This is the norm on the quotient space. Well, so we will have to show that this is actually a norm. So, well, before we proceed further, let me use some of the notations that you will commonly find. So, this is one of the standard notations which you will find in most of the textbooks. This is nothing but the norm on X mod Y, which you will find in most of the standard textbooks. Well, now let us try to prove that this is actually a norm, but before we proceed to showing that this is actually a norm, first thing that we will have to verify that it is well defined. Yes. So, how do you show that this is well defined? What do we mean by it is actually well defined? By well defined, we actually mean that this is actually greater than or equal to 0, right. So, is it actually greater than or equal to 0? The answer is in fact yes. So, first thing is that, so observe that norm of X plus Y, this is greater than or equal to 0 for all Y in Y, independent of whatever it may be, right. So, that will imply that this whatever you have, well, I do not have to write it as triple, because this is one of the node that is used in other textbooks, but what we are going to use is only this one. This is going to be bigger than or equal to 0, right, because this is true for all Y in Y, this is true, and similarly why is it a finite quantity? So, first thing again you can observe that 0 belongs to Y. So, that will imply that this, the way we have defined, is less than or equal to norm X, right, which is again finite second, right, fine. So, with all these things, let us proceed towards showing that it is a norm. Fine. Now, first property, norm of X plus Y, if this is 0, in fact X mod Y, if this is 0, we will have to show that this is the 0 coset, because that is the 0 element of this space X mod Y, right. So, if you say that it is 0, that will imply that this quantity, the infimum of norm of X plus Y, such that Y in Y, this is 0, right. So, what does it mean by the infimum is 0? So, what do you mean by infimum is 0? So, given epsilon positive, So, what we are going to show is that given epsilon. So, we will start with an epsilon positive, let epsilon greater than 0, then norm of x plus y, well sorry not norm of x plus y. So, there exists y, well, which depends on epsilon in y, such that norm of x plus y, this epsilon x, this is less than or equal to norm of x plus y, x mod y plus epsilon. But then our choice of this is actually 0, that means norm of x plus y epsilon x, this is less than or equal to epsilon, right. So, for every epsilon positive you have this. So, what does it tell us? So, this tells us that this x belongs to capital Y. Well, how does it follow that x belongs to capital Y? Well, so this in fact tells us, so this will imply that, well, in fact, so we have for each epsilon. So, in particular for each n in n, there exists y n. Instead of writing it as 1 by n, I am writing it as y n in y, such that norm of x plus y n, this is less than or equal to 1 by n. So, that means the sequence x plus y n converges to 0 in x. So, once you know that x plus y n converges to 0, that means that, so this will imply that x belongs, so this will imply that, this will imply that, imply that x plus y n minus y n converges to x. So, x plus y n, this converges to x, so which will imply that x belongs to y, because the limit is already in, so this limit is already in x, so which means that x belongs to y, right. Now, for the other part, what is that we wanted? Well, the other part is easy in fact. So, if x plus y is the 0 coset, that means what? That means x belongs to y. So, that will imply that x plus y is equal to y. So, that will imply that distance between x and y is same as is equal to 0, because x belongs to y, right. So, which will imply that the corresponding norm is 0. That is it, done. We are done with this. Right. So, we have shown that norm of x plus y is 0 if and only if x plus y is the 0 coset, right. And then the homogeneity, that is trivial, I do not want to go into this. The only thing that is left with is the triangle inequality. Right. Let us prove this triangle inequality. Let x plus y, well, x1 plus y comma x2 plus y belong to the quotient space. So, what we wanted is norm of x1 plus y plus x 2 plus y is less than or equal to norm of the first one plus the norm of the second one. So, as usual, so we are going to make use of the classical trick. So, please observe this, this is one of the important ones. Whenever infimum appears, this is the trick that we are going to make use of. So, start with an epsilon positive, then there exists y 1 and y 2 in y such that norm of x 1 plus y 1 is less than or equal to norm of x 1 plus y, as and well the first one is in x, the second one is in x mod y plus epsilon by 2, and then norm of x 2 plus y 2 as an element of x is less than or equal to norm of x 2 plus y 2 y plus epsilon by 2, right, that is it done. So, we are done, right. So, how are we done? So, now what we wanted is x 1 plus y plus x 2 plus y as an element of this quotient space, but then if you look at the way the addition in the quotient is defined, that will tell you that this is going to be x 1 plus x 2 plus y in the quotient space, right. Now, the distance or the norm on the quotient space, it is defined in terms of the infimum. Now, we have chosen y 1 and y 2 based on this epsilon, and y 1 and y 2 they belong to y, and y is a closed, in fact, it is a subspace. Therefore, y 1 plus y 2 is also an element of y. Therefore, this is less than or equal to norm of x 1 plus x 2 plus y 1 plus y 2 by definition of the quotient norm on x mod y. Now, this is same as, well, now use the, well, before that this is same as x 1 plus y 1 plus x 2 plus y 2. I have just reshuffled it. Now, use the triangle inequality on x, you will have less than or equal to x 1 plus y 1 plus norm of x 2 plus y 2 . Now, use these two inequalities whatever we have proved, maybe I will call these as 1 and 2, so that I will have less than or equal to norm of x 1 plus y x mod y plus epsilon by 2 plus norm of x 2 plus y in the quotient space plus epsilon by 2. In fact, this follows from 1 and 2, right. So, which is same as norm of x 1 plus y as an element of the quotient plus norm of x 2 plus y as an element of the quotient plus epsilon, and we are done. So, now this is true for every epsilon positive. So, this is true for every epsilon positive, which will imply that norm of x 1 plus y plus x 2 plus y is less than or equal to norm of x 1 plus y the quotient space plus the norm of x 2 plus y element of the quotient space, right. Fine. Having said this, now let us go to the next one, what is known what is about the convergence of sequences in the quotient space, right. So, let me put it in the form of a theorem. Right. So, let x n plus y be a sequence in x mod y. So, I am not defining what is x and what is y, because it is already clear. We are in the setup of quotient spaces where x is a nonlinear space and y is a closed subspace, right. So, you have a sequence, then this x n plus y converges to x plus y. Well, this convergence is in x mod y, if and only if there exists a sequence y n contained in y such that x n plus y n converges to x, right. So, this is the main theorem. The proof, well, the proof is not a difficult one. We are going to make use of the standard proofs. The proof is not a difficult one, all the standard tricks, whatever you have, whatever in fact known to you, you are going to make use of it, right. Let us do the forward part. Suppose that x n plus y converges to x plus y, right. So, you need a sequence y n. So, how to produce that? So, let epsilon greater than 0, you start with an epsilon greater than 0. Now, x n plus y, it converges to x plus y. So, then there exists n naught and n such that norm of x n plus y minus this x plus y, you can make it less than epsilon, in fact epsilon for all n bigger than or equal to n naught, right. So, this is one part, right. So, this in fact is equivalent to writing that x n minus x plus y, you can make it less than epsilon for all n bigger than or equal to n naught, right. Fine. Now, once you know that this is less than epsilon, by the definition of quotient norm for each n in n, there exists y n in y such that norm of x n minus x plus y n, this is going to be less than epsilon by 2 for all n bigger than or equal to, in fact, well, I should write it here, not for all n, in fact I will have, because the above inequality is only for n bigger than or equal to n naught. So, you will have only for each n bigger than or equal to n naught, there exists y n in y such that this is going to happen, right. well, I will have plus norm of x n minus x minus x plus y, right. This is in x mod y. So, I am insisting on this so that you will understand the difference between the norm on x and the norm on the quotient, right. So, let me call the first one as 1 and the second one as 2, right. So, only thing we will have to do is that so now that we have got y n's, so now only thing we will have to do is that show that these are the y n's that we wanted, right. Now, norm of x n minus plus y n, this is what we wanted. Yes. So, we will have to show that this converges to x. So, we have already started with an epsilon positive. Yes. So, we will have to show that this minus x is less than epsilon. Fine. So, now we are going to make use of 1 and 2. First, we will make use of this 2. This is norm of x n minus x plus y n. Yes. So, now let us make use of this 2 first. By 2 you will have this to be less than epsilon by 2 plus norm of x n minus x plus y, the quotient norm. But then from 1 we know that this is less than. So, what I will do is I will make it as epsilon by 2 here, so that things will be easy. So, this is going to be less than epsilon by 2 plus epsilon by 2 for all n bigger than or equal to n naught. That is it, we are done with what we wanted, that is it. So, thus in fact, this is equal to epsilon, that is it. So, thus x n plus y n, they converge to x, right. So, once you have a sequence x n plus y converging to x plus y in the quotient norm, you get a sequence y n in y which converges such that x n plus y n converges to x. So, this part we have seen. Now, let us go to the backward part. Right. Suppose that there exists a sequence y n such that x n plus y n converges to x. So, we will have to show that this sequence, the original sequence x n plus capital Y converges to x plus y in the quotient space, right. So, as usual let us begin with an epsilon positive. So, now what is that we have? X n plus y n converges to x. So, there exists n naught and n such that norm of x n plus y n minus this x, this is less than epsilon for all n bigger than or equal to n naught, that is it. So, this is the n naught that we are going to make use of. Now, what we wanted is norm of x n plus y minus x plus y, this is in the quotient space, right. So, we will have to show that this is going to be less than epsilon for all n bigger than or equal to n naught. Well, by the definition of addition in the quotient space, this is same as x n minus x plus y. Now, for each n you have an y n, right. So, once you have an y n, by definition of the quotient norm, this is going to be less than or equal to norm of x n minus x plus y n in fact n bigger than or equal to n naught, because we have n naughts only, well you have for all does not matter. So, now this is x n minus plus y n minus x, well this is not in the quotient space, this is in x. Now, if you use whatever you have here, let me again call this as 1. So, that this is going to be less than epsilon for all n bigger than or equal to n naught. This is from 1, that is it, and we are done with what we wanted, right. So, with this we have introduced quotient spaces and we have also seen the convergence in the quotient spaces. So, before we wind up, let us look at some simple properties of our general nonlinear space, right. Well, if you have looked at so called Euclidean spaces, the study of Euclidean spaces usually it is, there is another name, it is usually called as what is known as the rubber sheet geometry. Well, if you look at a rubber sheet, you can make it big or small as much as we wanted, because it is a rubber, you can, it is a kind of elasticity property, and that is the property that we are going to see, that it actually holds even in the case of a nonlinear space, right. In fact, so the first property is that for any x in x and r greater than 0, the ball with center at x and radius r, this is nothing but just look at the ball with center at 0 and radius r and then add x to it. You can translate it, just nothing, and in fact, well, so we will come back to it, the more general one can write, well this is in fact same as r times ball with center at 0 and radius 1 plus x. You do not have to do much, just look at the unit ball and then dilate it by r, then you will have the ball with center at 0 and radius r, and then translate it by x, what you will have is this ball, that is the whole thing. So, this is what I meant by the so called rubber sheet geometry. You can just pull it as much you wanted, and you can also just shrink it as much as you wanted. I will only prove the first equality, the second equality. So, what the B0R is same as R times B01, which you should be able to prove it, not a difficult one, right. So, we will show the equality. Let us begin with an element y from Bxr, right. So, let us begin with a y in Bxr. So, I will have to produce an element of B0R and then plus x, right. So, what is that element of B0R? So, how to produce that? So, I have y in Bxr, so that means what? Norm of x minus y, this is less than r, right. So, once I have x minus r, y inside is less than r, the norm of which, so that will immediately tell us that the norm of this x minus y is in the ball with center at 0 and radius r. So, this is one of the crucial observations, it might look trivial, but this is the crucial observation that one will have to make at this stage, right. Now, you know what to do. So, therefore, x, which is, I will write it as this way, x plus y minus x, that is it, done, right. So, in fact, so we wanted, sorry, not x, so we wanted in terms of y, sorry, we wanted y. So, therefore, y, which is I will write it as y minus x plus x, right, that is it, done. So, and this is in the first element is in, because norm of x minus y is less than r, the same thing will also tell us that y norm of y minus x is also less than r because of the homogeneity property. So, which means that this is in B 0 r plus x, that is it, done, we are done with what we wanted, right. Now, for the converse, so let me choose a y from B 0 r plus x. Well, by definition, so implies there exists you get an element y dash from B 0 r such that this y can be written as y dash plus x. That is it, we are done with what we wanted. So, only thing that we will have to show is that this y is in Bxr and that follows from the way we have decomposed y, that is it. So, now what we wanted is norm of y minus x, this is what we wanted, right. The way we have decomposed should tell us that this is y dash plus x minus x, which is same as, because x and x gets cancelled with itself. So, this is same as norm y dash, but y dash it is in B 0 r, therefore, this is less than r, and that is exactly what we wanted, that is it, done, right. So, this is the first property. Well, not only are balls translated, even open sets. So, if U is an open set and x in x, then U plus x is also an open set. Well, this follows from whatever we have observed, from this it follows, and therefore, once you have this, you have something more. What is that? That if U is an open set, and A is any subset of x, then U plus A is also an open set. Right. So, how does it follow that U plus A is also an open set? Well, it follows from, just write this U plus A as union over A in A, U plus A, that is it, done, and each U plus A is an open set from this, and once you have this, and we know that arbitrary union of open sets is also an open set from which this follows, right. Fine. So, here is a final observation which is not true in general for a general metric space, but this is true only in the case of norm linear spaces. Last observation, for any x in x and r positive, the ball with, look at the ball with center at x and radius r, take the closure, it is going to be the closed ball, all those x in, well, all those y in y, y in x, such that the distance between x and y is less than or equal to r. So, this is one of the main thing, in fact, one of the crucial observations, in fact, a property that is very specific for norm linear spaces. Well, so the proof is not a difficult one. Well, I will leave it as an exercise, I will simply call it as an observation, or that observation that this set, the set, all those y in x is that norm of x minus y is less than or equal to R is a closed set. So, this one should be able to show that this set is a closed set, in the sense that show that the complement is open, that should be quite easy to show. One should be able to show that part, that is not a difficult one. Now, let us go through, right. Well, this is a closed set, also the ball with center at x and radius r, this is contained in this set, because you have less than or equal to, and there you here in this set, in the other set you have a strict less than, therefore, the containment. The property of the closure is that it is the smallest closed set containing that set, right. If you have a set A, then A closure is the smallest closed set containing A. So, now I have the ball with center at x and radius r, which is contained in a closed set, and therefore, that will tell us that the closure of this ball is contained in right. So, we have one end, one part we have proved. We need the other way inequality or the other way inclusion. So, you start with an element y dash from this, right. What we needed is that we will have to show that this y dash is in the closure of this ball. To show that something is in the closure, the familiar way of doing this is to produce a sequence from this ball which converges to this y dash, and we are done. Yes, again the familiar thing what we are going to make use of is the fact that nonlinear spaces, they behave like a rubber sheet geometry, that is the whole idea. Well, so we need a sequence. So, consider this. So, let y n dash equal to 1 minus r upon n times y dash plus x upon n, right. So, this is the sequence. Well, we have not done much. So, what we wanted is that as n tends to infinity, so we needed y dash, and when you subtract it from x, we need it to be less than r, because you wanted it to be inside this ball, that is the whole idea that we have made use of, right. Not r by n, sorry, we wanted it to be 1 by n, sorry, yes, yeah. So, we wanted the whole thing to lie inside, so for n in n, that is it. So, now is that we wanted this to lie inside this ball. So, distance between y n dash and x, this is what we wanted, which is same as distance between 1 minus 1 upon n times y dash plus x upon n minus x. Well, if you collect the terms, this is going to be norm of first term is 1 minus 1 upon n times y dash plus again 1 minus 1 upon n. So, I will have a minus here, right, times x, that is it. So, just pull them out, pull this 1 minus 1 upon n outside, which is a positive quantity. So, therefore, you do not need any modulus, and the remaining is going to be y dash minus x. Well, remaining is not y dash, sorry, I do not need a y, right, remaining is going to be y dash, right. So, now this norm of, so this is going to be less than or equal to 1 minus, because y dash belongs to this set, its norm is less than or equal to r, but then 1 minus 1 by n, this is a quantity which is strictly less than 1, and therefore, this is strictly less than R, that is it done. So, which tells us that this y minus y n dash they belong to BXR, that is it, and it is clear that these y n dash also y n dash they converge to y dash as n tends to infinity, that much is clear, that is it. And therefore, so that means y dash belongs to BXR closure, that is it done, that is exactly what we wanted, we have proved the other way enclosure. So, with this let me stop this lecture. So, in the next lecture we are going to see an important class of examples for non-linear spaces, what are known as the inner product spaces. You can send your feedback to the following email ID. Thank you.